good to see everybody online and in person. So we're very excited to have Chee-wooi 10 and Junqiao Qiu today for a joint seminar.
Hello, everyone. How are you doing? My name is Chee-wooi 10. I'm from Electrical and Computer Engineering Department. I want to talk about attack combination from the power engineering perspective and hope that it will give you some perspective. Before I start, I want to get to know the audience. How many of you are computer scientists? Okay, so my guess was right. So everyone is computer scientist. I'll make sure I talk more linear toward that. So this is a first picture that probably is no stranger to you. It's a map of the United States. And you know, as you can see, Texas is by its own, and then Western interconnection and then Eastern interconnections. We have been part of the Eastern interconnection. So whatever happened in Florida will probably all the way up to Michigan Houghton if there's a swing oscillation occur in the system or any kind of disturbance. The picture on the top right show you the complexity of the transmission circuit. So this is pretty much the transmission cover. When you travel across the country, you see the big tower that looks like a high voltage. This is exactly this. And I think that show you that the voltage level can be up to 765 kV, 765,000 volt transmission circuit. So it's very different than the circuit that we had from the outlet. So basically what we do here is power would lost as it transfers from one location to the other. So what we do is we step up the voltage as high as possible. As a result, the current will proportionally reduce. As a result, the loss of power can be minimum. So it's like, you know, you increase the voltage, the current will get smaller, and then eventually the power will get to us as you step down to distribution system, and then eventually residential, and then our outload here. What I want to bring across the message for today is there is a control system in power grid. We call it SCADA network. In layman terms, is control network that is centralized in the hierarchical structures. You see that what the map on the top right is can have hundreds of control areas, meaning that it's like different area, there's a different transmission utility. They all operated at their very different way of how they want to secure the reliability of the system. And one thing in common from this is for sure, we are interconnected, meaning that whatever happened in, say, New York, go all the way to Florida, or maybe in Montana under this circumstance. So the theme of why I want to promote here, although it may be related to the physics of the grid, but I want to say that the cyber attack is really raising the concern here on the power grid, even though it is a private network that we're talking about in operational technology network, OT network, or IT network. And you probably may heard a lot in the recent year that the ransomware that's actually getting to us and how things will change. While the nightmare scenario would be if we get ever to the power grid, it can cause some problem when the switching action is being manipulated by the back actor that get into the control system that could potentially initiate the blackout. As you may know, the power grid is actually designed in the way if there's overload, the circuit breaker will trip, and as a result, cascading may happen. So there were tens of thousands of substations across this map. So this is a control center that show you the situation awareness in the control center. So what basically it means is you centralize all the measurement coming from different geography that have the measurement value coming from substation that measure power, reactive power, active power, voltage, is all in three-phase. At the same time, give us the digital measurement in terms of the things coming into control center. While under normal condition, these people, operator in the control room may be relaxing, sipping coffee, looking around the better forecast. But when there is a disturbance, and now what I mean by that, it could be a storm walking through a certain area of the control area, the dot metric printer is still there. They're printing out all the alarms coming from this substation just to promote the awareness of what's going on this day. And then all the screens showing alert coming in and out. So the people of the operator will have to figure out what's going on within the system, and potentially searching for the root cause of the problem that trigger the circuit breaker trip that potentially lead to a problem. This is a picture diagram, came from all the way to 1967. We call it security state transitions. Now, there is a original traditional sense of security in power system, and the cybersecurity that we are going to refine in the future. So the security state of the transmission circuit is that we have this secure and insecure, and the resource emergency. Basically, what it does is that if a transmission circuit is being tripped, we want to see the state of the entire power grid, whether or not it's insecure or in emergency. So emergency means that we have overload in other circuit, and the implications of that emergency, it will lead to potential other cascading outage. And as we all know, the power generation and load is constant. While we are losing the transmission circuit, that means the transfer capability within a power grid will be losing, and we could potentially losing the entire system gradually if we are not doing a remedial action in a timely manner. So that's how that restorative come into picture, that will shed some load to balance the generation and load under a certain part of the frequency. Hopefully it will bring back the grid to the normal condition. This is a much more sophisticated network, but basically this is, again, a centralized framework that getting the data from state estimation. And then we have this online load flow analysis, which I highlight in the two major red box, that indicating that the telemetry meter, the data coming from 100 of substations. So I'm speaking about as a one transmission utility that could have maybe 300 substations they are monitoring under their territory. We published a framework, originally, we call it RIN framework, is to gather the physical event, alarms event from this diagram. At the same time, we also say that in this new edge that we introduce cyber infrastructures, the security law event that of anything related to the substation can be gathered to do some sort of correlations that will be able for us to see what are the anomaly that we can infer to, and perhaps doing some sort of impact analysis, which is referred as cyber-based contingency here. So this will allow the operating control room and see what are the combinations out there will lead to some potential problem. And then eventually will allow them to make some decision, an informed decision, hopefully will make fast enough to perhaps save the system from cascading further that will lead to either brownout or blackout of the region. And so all of this is related to power system analysis here, but what is really at stake here is the cyber system. Now this thing in the control room is all IP communication. So it's not like in the future we have proprietary information. Everything now is IP-based communication. So the cyber anomaly and the physical consequence of the, in terms of circuit breaker that connect to each substation will have to be understood in terms of the dynamic and what are the potential consequences. In this case, the nightmare scenario on the transmission circuit is we don't want the grid to become a blackout. So we have to understand what are the potential alarm and as well as the anomaly in the system. If you look at this picture, we have a wide time horizon that came from National Academy that back in 2013 that show you the broad spectrum on the 90s, came from computer virus all the way to Trojan horse, all the way to sophisticated attack scenario that we have today. And 10 years ago, if I told people that we have a drone that can create electric short circuit in substation, people might think that I'm insane. But for today, the drone is actually more powerful than what we could do. And I'm just spelling out one possibility. And certainly from a cybersecurity subject is that we're talking about malware propagation from network to network, from less trusted network to the more trusted network. It will eventually go into the OT network, and then who knows that there will be a ransomware that we are worried about is that will trigger, that will disconnect n number of substations. So those are the changes that we actually experiences over this year. And so from the data for data injection standpoint, then you have the SCADA and you have the malicious actors that will be successfully hack into a certain substation and make some value chain of the system. So the centralized framework of the SCADA will have to be verified on how this is being done in terms of the collecting some of the temper data measurement. A lot of this assumption in the literature in academia is that they make an assumption that the intrusion just happened. And as a result of that, this can be manipulated by the intruder electronically that will allow them to change the state of the system, and perhaps it may screw up the electricity market. And the things that what we are addressing here is has to be compromised endpoint. And some of the risk aspect is man in the middle of attack may not be so easy, but intrusion electronically, whether or not it's done by a human being or software agent, this day might be possible. So this is a conceptualization of all of this my map. So what I have mentioned earlier that there's a contingency, power system security. What I refer to is this is a map of the power grid in a more smaller portion as compared with the first one that I showed you earlier. That the red color, say, for example, tornado walk through it. What we do traditionally, we make sure that the grid will be able to withstand the disturbance if this line is being tripped, and we check all the state of all components around the power grid and to see if they are overloading condition or low voltage. This may not be done in the more exhaustive manners because N-2, if you look at the storm trajectory walk through a certain part of the geography, it may be selected based on the configurations of the network. As you can see here is basically the tower of carrying the two circuit on the grid, we call it N-2, will be analyzed. And sometimes we might do this here and here, but not for this and that at the same time because they are not in the vicinity of the storm. So the real threat is all this node that we have here is called substation automation system. Assuming all of those substation automation in the system, then if a hacker successfully hack into the system of this substation, it would translate into, if they electrically disconnect all the switch gear using the local control system, that will translate into N-14. So this has never been what we expect to in terms of designing the power grid to withstand that. And so certainly that's not something we want to build more lines just because we are afraid of cyber attack. A lot of this will have to deal with investment on security technology. But what my talk today is to show you the possibility in terms of the attack possible that get into a substation. If this is 14 N-14, if there's a two coordinated attack hack into other substation at the same time, it will translate into N minus, I don't know, 20, N minus 30. As a result of that, if this is done, it could actually trigger the grid that could potentially lead to instability that have a blackout. So this is a picture show a substation detail on remote lock-in, and you have all this computer system and IED that have physical connection to the switch gear. And you can see that little box here is the circuit breaker. Any of the control variable here can be done through the local human-man interface here, as you probably can see. So what I want to do here is to show you the S selects one condition. So we start with the modeling on the cyber aspect. So as you probably see, this is a cyber physical problem, right? You have a cyber intrusion that will hack successfully into a system. And what we want to do is we want to capture the existing deployed cybersecurity technology in substation that include firewalls. And in this case, we use a stochastic pre-trained to capture that. And the rule what we can say is that in the OT network, we simply deny everything and then especially allow certain port to go through. Unlike in the IT world, it's the other way around. So we carefully do it, abstract this data from each role and correlate that under this setup of the configuration network. And the other model that we do is to model the computer system, right? If there is a password field lock-in, just like what we have today, that could potentially be a malicious activity that could be attempt by the malicious actors that could potentially contribute to the success of the hacking in the process. So we have that basic model capture early state to describe the computer system and the firewall. And as you can see here is that the PetriNet model will translate that high level abstraction into the reachability graph, as you can see here in this. So to simply put, what we've done in the past is we do one substation at a time under this publication some time ago that will allow us to do combinatory assessment later on. But the idea here is if we gather all this anomaly across different substations, we should be able to capture the cyber system just like that. And here is the detail of how we quantify the risk and the impact of the substation if the substation is being hacked. So S-1 contingency meaning that if the attacker successfully hacked into the substation, the nightmare scenario will be they will be able to disconnect electrically using that compromised system under that substation. As a result, we want to quantify that impact together with the risk steady-state probability that we abstract from the PetriNet model. So those are the coming from this, and then is coming from that. So that there's a different network topology we described. Now you may ask, the combinations of and select one makes sense, right? Because you have a cyber system that potentially get into that. What about multiple substation hacking? If you look at originally we have the N-1, it's all based on the storm trajectory, how you walk through the geography, right? So you could not have N-2 unless the storm happened at the same time on the different location, then we can do exhaustive enumeration on that. But for IP-based substation, if we have all the substation is IP-based and all the substation have remote locking feature, then it will potentially lead to many combination complexity that could allow us to do more analysis. So this is the work that we later on we include into the picture to capture more footprint of the malicious activity coming from not only the intrusion attempt, but at the same time the setting of the relay chains, potentially some of the malicious switching action that lead to some outage. So these are the temporal correlation that we did also with respect to. So I'm going to go through this really quickly to show you how is that possible. So in this case, we could have 4 substations at the same time, and how we want to capture the impact as well as how to do the ranking enumeration. Because as I said before, if all the substation can be remotely locked in, so as a bad guy, so we have to account for the possibility of this combinatorial evaluation as part of our analysis. As you probably can see that 61, 64 would have all combination into this. So this is just to give you an idea of how we do analysis, and what we do eventually is to take full advantage of the power flow analysis. Power flow is a well popular tool that we use in a power system to evaluate state, and we sometimes use the convergent or divergent to determine if that combination of case could be problematic. So to simply put, the divergent is where we figure out if that combination is bad combination or not good combination. So we did actually going through some systematically from S-1 to S-K to make sure that we have the substation enumerate, and then so eventually as we go higher on this evaluation, the total combination may get higher, but we actually eliminate those combinations we already spot out here. As a result, we can systematically eliminate some of the combinations we already figured out earlier. As a result, we can find out more unique combination as we go higher of the combination. So as you can see that under this circumstance, you had 37 we have to use to evaluate. So that is the combination perspective. And this is a diagram I thought I should show you guys about the how power system outage would look like. To say hypothetically, if not one of the Northeast system that has been hacked and being compromised, and then attack had been done at the 3 locations of the substation in the geography, these people in the control room will certainly get some input from in terms of alarm coming into the system, because circuit breaker opened, and some of the alarm information it was set in the logic on the control system will come all the way together. And this is one thing, but the grid itself have to balance the total generation and total load. So that cascading effect will really kick in later on. That's how we are worried about in terms of the balance of the total load and balance of the total generation, is because when you string the transfer capability of the grid, then a lot of this protective relaying is being set out locally, is just doing what it was originally told. So meaning that the threshold value or the relay setting and all that is done it locally. They have to treat. There's no coordination. It's just purely simple relaying business observed from a local. So that's how a lot of this cascading happened, is because when you want to protect the expensive equipment locally, but at the same time, you want to protect our economy, then you will have to make sure that all of this well balanced, and sometimes we come up with that special protection scheme that we want to deal with. But for the interest of time, I will be more than happy to tell you more in terms of the ongoing research I have. I just thought half an hour that will allow to go as far as I would like to today. But possibility is really the key here, what we want to get into in terms of evaluations of combinatorial to as many combinations as possible while keeping the combination. So with that, I think I will stop here for questions.
So we're going to do a joint Q&A at the end with Junqiao and Chewie. So make sure you stick around and save your questions that you had for Chewie. I know we had some hands raising at the end here. Very excited to hear from Junqiao Qiu. Thanks, Chewie, for the great talk.
Well, I'm so glad to have the chance to talk about my research in unleashing the power of parallelism. Today I will mainly talk about my current project in extracting the fine-grained SIMD, the single instruction multiple data parallelism from the data-intensive computations. Okay, so before we dig into the research topic, I would like to briefly introduce myself. Currently, I'm an assistant professor in computer science. My research interest is just like the title in the previous page said, is in parallel computing. And I will provide 2 courses, computer organization and high performance computing. And thanks to the NSF support, I have multiple opening research positions in my lab for both undergraduate and graduate students. So if you are interested in doing research in parallel computing, so just feel free to contact me. Okay, so go to the research topic. So as many of us have observed, nowadays we have parallel processors in almost every computing scenario, from smartphones to self-driving cars, from IoT devices to virtual reality, not to mention the supercomputers in national labs or the computing servers in the cloud. How to effectively utilize this increasing hardware parallelism becomes so critical for the high efficiency and high scalability of our software applications, especially considering that the value of the data to be processed is usually huge. For example, the data generated from the IoT devices, the banking transaction or purchasing history, or the interactions within millions of users over the network. But before we think about how to effectively utilize the hardware parallelism, the first and the most important question is, can your computations run in parallel? So unfortunately, there are a large group of computations that are extremely hard to run in parallel. So we can take a look at these 2 very simple examples. On the left, it is a loop that adds a constant b to every element in array A. If we unroll this loop, it is easy to see that different iterations can be executed in parallel. Each of them just updates an array element based on its values or based on its previous values. So we say this kind of loop is naturally parallel. But if we take a look at the other example on the right, after unrolling, each instruction also updates an array element, but based on the value of the prior element. In this case, we cannot simply run different iterations in parallel. And if we do so, the final results will be incorrect. This is due to what we know as the loop carry dependence. And we say this kind of loop is inherently sequential. So one of my research interests is to reconsider such inherently sequential computations and find the possibilities to parallelize them. So in this talk, I will first introduce how to utilize the fine-grained parallelizations for finite state machine-based computations. And then we will go further to see for the general computations, how can we get benefit from this single instruction, this fine-grained single instruction, multiple data vectorization. And finally, I will briefly mention some of my future work. First, what is finite state machine? We may recall this from our undergraduate course, like the compiler, automata theory, or the digital circuit design. So finite state machine can be, finite state machine is an abstract computation model with some states and transitions. The transitions can be represented as a directed graph, just like the upper right shown in this slide. So the finite state machine starts from an initial state, and each time reads one input character and make a transition. The example here in that is for pattern matching. So each time it reads an input character, and then if it enters an accept state, which is the state denoted with double circle in the transition graph, and then it report a match, the match of the represented pattern. But in fact, finite state machine has been widely used in a lot of areas, like the databases, web browser, hardware design, and I believe it has been also used in the power system, just like we can see in the previous talk. And so considering the fundamental importance of finite state machine in computing theory and its broad range of usage, I think it will benefit a lot if we can effectively parallelize the finite state machine computations. And if we take a look at the codes, usually we will implement the finite state machine computations as a loop. So in each iteration, the current state will be updated depends on the previous state and the current input symbol. So clearly, there's a loop carry dependence, which prevents it from running in parallel. So to break the dependence, a very natural idea is if we can split the input sequences into 2 segments, and then we run them in parallel. It's quite, we know that for the first segment, the starting state is the original starting state. But which state should we use for the second divided segment? It depends on the execution results of the previous one. So in fact, this is the dependence, right? So to break this dependence, maybe we can use the speculation. We can guess, okay, maybe the starting state for the second segment is state 2. If the prediction turns out to be correct, then we have finished the whole processing. Otherwise, we have to re-execute the second segment to ensure the correctness. So this is known as the speculative parallelization. It breaks the dependence by using speculation and then relies on the verification and re-execution to ensure the correctness of the final results. But in fact, if we take a look at the entire design, existing efforts, in fact, they just explore the coarse-grained parallelism, which means they only work at the thread level. And so that they can achieve at most n times speed up when running on an n core machine. But if we considering the fact that the modern microprocessor, it features features a variety of hardware parallelism, from instruction level to the on-chip multiprocessors. In fact, if we want to further boost the performance of finite state machine computations, we should introduce the finer grained parallelism to release the full power of modern processors. So in one of my previous research, I introduced the single instruction, multiple data, the SIMD parallelisms into this finite state machine parallelization. In modern CPUs, a primary example of SIMD parallelism is what we call the vectorization or vector instructions. So this vectorization was originally designed for the floating point computations in the scientific codes. We want to use some special instructions that execute elementary operations such as addition, multiplication, subtractions, etc. But we want to run them in parallel so that we can have the better performance. So for example, here, for the given two vector A and B, so the vector result C will be produced by just using one SIMD vector instructions. The addition vector instructions here is provided by Intel. This is what we call the SIMD intrinsic. So it indicates that the vector size is 128 bits, and each element can be 32 bits. That means we can run over 4 elements in parallel. So in the past decades, the modern microprocessors, they provide multiple generations of SIMD intrinsic. Each of they will be either increasing the vector width, or they provide some newer computational capabilities. Just take Intel, for example. So they provide the SSE for 128 bits vector instruction, and then they provide AVX, which is 256 bits. And in the most recent architecture, they provide AVS 512, which is, of course, 512 bits for these vector instructions. Of course, there are a lot of criticisms, for this AVS 512, but that's another story. Then in the latest architecture, they also, the Intel also provide a kind of the SIMD intrinsic for, especially for specialized for the deep learning. So with this fine-grained SIMD parallelism, in fact, we can get significant performance improvements for our applications, just like the figure show here. In fact, the purpose of this SIMD vectorization is try to introduce the fine-grained SIMD hardware parallelisms in one core. And the multi-threading, on the other hand, is try to use the coarse-grained, all available cores on the processor. Then go back to our finite state machine, based computations. If we want to introduce the fine-grained SIMD vectorization, we first unroll the loop with speculation. So the unrolling factor here is 2. So in fact, the last two instructions here, they indicate that we execute the finite state machine computations over the second divided segment with speculation. Then we change the order of these instructions a little bit. The interesting thing is we find the first two instructions, they execute the same operation, but of course on different data. And the last two instructions, they also have the same operation, but on different data. This is what we call the single instruction, multiple data. And finally, we replace these scalar instructions with the corresponding vector instructions. And our result shows that we can have 4 times speed up over the baseline, which just use the coarse-grained multi-threading. We have known that by introducing this fine-grained parallelization, we can have significant performance improvement in the finite state machine-based computations. Then the next step is, can we bring the benefits to the more general computations through this SIMD vectorization? So, as our software developers, of course, we can hand code the SIMD vector instructions. But if we target on the general computations, the hand coding is a kind of tedious and error prone. So a very natural idea is we use the compiler auto analysis and optimizations to introduce those fine-grained SIMD parallelism. So the existing compiler techniques, they will first check the current computations, whether they are naturally parallel. If they are, then the vectorizations will be quite easy. And there are mainly 3 directions. Again, we can use this very simple loop as an example. So it is naturally parallel. Each iterations just put some results of elements in A and B to array C, and put the results of D and E to array F. So the first direction is loop vectorization. We first unroll the loop, and then we combine multiple instructions across the consecutive loop iterations into one SIMD instructions. And then the second mapper is what we call the superword level parallelism. The key idea here is, instead of unrolling and looking across the loop iterations, we just focus on the instructions in the same loop iteration or in the same basic block. In this example, we find that in the loop body, we have 2 instructions, and these 2 instructions, they execute the same operations, but on different data. Then we just replace these scalar instructions with the corresponding vector instructions. And we can, by using this fine-grained SIMD vectorizations, of course, we can improve the performance, because now we reduce the number of instructions to be 1, from 2 to 1. Then another increasing popular approach is what we call the SPMD on SIMD. The key idea is we just make the different instance of a kernel to the single SIMD vector instructions. It is similar to providing the GPU programming model onto CPU. And our the finite state machine vectorization we discussed about, in fact, can be considered as a special case for this compiler approach. But due to the time limitation, I won't provide too many details here. But if you're interested, we may discuss that later. So we have discussed that we can see that the compiler techniques can provide the SIMD vectorizations to the naturally parallel computations. But the problem is, if the computations are inherently sequential, the above compiler techniques won't work anymore. So what we need to do is we have to break the dependence. So the idea here is we use the speculation techniques we have introduced in the finite state machine parallelizations. We use the speculation to break the dependence at first, and then we apply the existing compiler auto vectorization techniques. One example here is we have a loop, and then we find that we have multiple execution paths in this example. And only the second path, execution path, P2, will carry dependence, which prevents the entire loop from running in parallel. But if we can guess, or we can speculate that 99% of the computation, they will run over the execution path P1. then which is naturally parallel. And then we can simply remove the second path and use the above compiler vectorization techniques. And then we can, of course, we can have better performance. But we also need to check the accuracy of our speculation, to ensure the correctness of the final results. Another example is if we only have one execution path and it always carries the dependence, just like the example shown here, a variable s carries the dependence. So to break the dependence, we can guess the value of this s to break the dependence. This is exactly the same as what we have done in the finite state machine computations. But the problem is we are talking about the general computations. The value of this s can be any number, which seems impossible to make a guess. Interestingly, I find that there are a large group of computations, especially those computations on, on the binary sequences. Only several bits in that variable will carry dependence, and all the other bits, they are either constants or they won't affect the desired outputs. So with this observation, we find that it can give us great chance to make a speculation to break the dependence and then introduce the fine-grained parallelization, and thus we can improve the performance. Now we have talked about how to use speculation to break the dependence, and then how we can introduce the fine-grained parallelizations to improve the performance. So finally, I will briefly mention some of my future work. So in the short term, I will still focus on parallelizing the data-intensive computations, in particular, the finite state machine computations and the big stream processing. And I think the key idea is about how to utilize the massive parallelisms on GPUs to parallelize those inherently sequential computations. And the second idea is I would like to develop multi-objective optimizations, because we know that in real-world data processing environment, our developers have to consider multiple objectives. For example, the energy, latency, throughput, and even accuracy, and of course, energy. And then I think that would be great if we can develop a framework which can automatically optimize the applications based on the given objectives. And in the long run, I would like to connect my research to the frontier of other domains, such as deep learning, cloud computing, and security. And I also believe that just like architecture design, to gain sustainable performance benefits, the future program optimization should be more domain specific. Okay, I think that's it. Thank you so much.
Do we have questions? All right, so I'll lead off with a question. So, I think that one of the big challenges in what both you guys do is that it's pretty fundamental to the hardware to make progress, right? So how do you see these kinds of techniques being rolled into future CPUs and future power grids, and how much do you have to do before you can actually create something that then is, how far away is that stuff, and what's the path look like?
Oh, okay. In the power energy society, I think if there's a spectrum of how we will balance practice versus theory, I think we were lean toward on the practice. And with today, in terms of the supporting infrastructure in the control room, I think we have every state of the art that we need to, except that moving to the cloud, I think is a little bit tough sell because of conservative in terms of how this utility want to manage their own data rather than giving, say, for example, Google to manage all the data from around the world. But I wouldn't say that that would be an immediate, that would say this would be an immediate barrel, but who knows that one single good business case could change everything. And as you probably may know, Facebook now they come up with a new name with emphasis of interoperability. And I think that Power Grid has been the trend over the last 15 years in terms of having a different software interoperable based on a certain type of the communication protocol. For the research I'm doing is more on the planning, how we can optimize and there's combinations of complexity. We can take full use of what he's doing in terms of parallel, put everything in the cloud and maybe run it for a few days. If the parallel computing works just fine, I think we will have a pretty comprehensive result and accurate result rather than the single thread processors to run it for a whole month or so, something like that. So that would expedite that, but there's no real-time urgency. But I'm sure that there might be some real-time urgency. Like for example, this day in mainland China, they have the notions of faster than real-time, which emphasize a lot on the digital twins, that we create infrastructures that are close enough to the physical real world, and they want to establish a framework to predict what could be a potential catastrophic event and do a quick preventive action to prevent that event. That's why if you realize that I put the evangel picture in the end, the combination and all that, that's the sort of the things that I think in not only in the superhero movie, but I think it's a dream of research. We want to predict the future as fast as we want. And I think that's the merit that we share here in this, in terms of how we can make things faster.
Yes, from my point of view, I would say, the future architectures, as I mentioned here, they become more and more domain specific. For example, for a specific kind of computations like deep learning or some others, they will develop, the architecture guys, they develop a kind of specific, machines for those kind of computations. And I would say my research mainly in the compiler part. And my idea is, for these emerging architectures, if I have those architectures and I want to get those benefits of these new architectures for the other kind of computations, what we need to do is in fact to develop an efficient infrastructures to first analyze the properties, the features of the applications we're talking on, and then try to see how we can utilize, how we can transform those computations to fit well on the emerging architecture. So I think this will be a very interesting direction. And and again, I think the processors become more and more parallel. So how to efficiently utilize the parallelisms also very important, especially for those what we call the inherently sequential computations. How to break the dependence, in fact, is also a kind of domain specific. You never know what kind of dependence they are. So,
Thank you for the presentations. And my question is it might be general, but you mentioned in your slide that future computation might be domain specific. But my question is, in the future, there are a lot of major areas that are basically connected with each other. For example, you might need to use VR with deep learning and at the same time have a security. And in that case, how can we specify the architecture? For example, if we use one of the specific architecture or computational power for one of them, then we couldn't work for the others area. So how would we handle that?
Oh, that's a very good question. So in fact, first, when we talk about different domains, we will not just focus on where it comes from. We can spend sometimes on analyze the features of these computations. For example, for the deep learning, I think the time dominant part in that is the matrix computations. So we can focus on the underlying the computation models And then we pick out the features of these models. And even for computations from different domains, they may share the same computational patterns. So by analyzing these patterns, we can figure out, okay, if the different application, they share the same patterns. So one application can reuse the architectures, which is specially designed for the previous computations. So I think that's where that will be one of the directions. Just take a look at the underlying, the basic computation pattern, and then we can get a lot of hints and ideas to accelerate and improve the performance.
And I share the sentiment because I think in electrical engineering, we often use topology as to store information in a matrix, and often that if you have a fat matrix of say 10,000 by 10,000, and sometimes how you sort the matrix in a way how to decouple certain part and remove the dependency so that you can do it as in a smaller chunk. That's often the art of that, how we can parallelize with the resource we have today. So this is a really interesting world in terms of what are the platforms, particularly the GPU, as probably has been the recent trend. Many researchers work on parallel computing using GPU computing power. I first thought that it was graphic related, but then this is on other domain of the applications.
Well, we have time for about one more question. Anybody in Zoom have a question?
Yeah.
So one question specific for Chee-wooi. So I think that for your research, it's difficult to do innovation in your work process.
Are you talking about validation, right?
Yeah.
Well, that's what I brought out the word digital twin these days. Even there's a word company called RTDS, real-time digital simulator, or a Canadian company called AlphaRT. What they do is they are selling this hardware and software together to mimic as close characteristic of the power system without building a real one. As you know, the whole power system is the whole country. and so this is a trend not only for power grid, but if you remember the nuclear power plant, they also trying to do the same thing now this day as we are trying to explore a potential nuclear facility, and happen to be attending some of the section in the recent year that I learned a lot of things that people want to replicate that digital twins on the physical characteristic, and so validation might be we already have some existing tool, but there's still a computational challenge, as what we have in terms of engineering is we build a model, and then this day we have data driven. So there's a data driven coming in, and sometimes the model itself is incorrectly established. So the data driven might be refining the model. So these two are closely dependent. In the past, what we usually do is that the model must be right and the data should be wrong. So we put more weight on the model, but I think the future trend will be interdependent, the data driven versus the model. And that's why I'm here as an engineering faculty reaching out to computing, because there is a need on many programs in the country. Like NSF, they have cyber physical system. It's not just a electrical aspect, there's a lot of implementation that require computer scientists like you guys to make it happen. Like, I remember there was a CPS on the satellite going to Mars. So there's a Caltech faculty demonstrate how they interact with the machine in the satellite, avoid it, flying to Mars, and that require not just understanding the computer science part of it, but also many different science involved surrounding. And I thought that even same thing for transportation system, like this thing, you have to implement computer systems in the car. So this cyber is not just a word, it's really implementation.
Awesome. Well, thank you so much.